Okay. All right. The section we're in is 10-2. It was central angles and arcs. We talked about this last Friday. I think Friday we did the example where we used the globe. We were trying to figure out like positioning on the globe and trying to figure out distance between cities using a simple arc length formula, which is one of the properties. The goal today, we have two properties I want to cover, and then go right back into talking about how do we use it. Like what are examples of homework problems? What are like real life examples, like practical application problems you can actually use this stuff for? Not just the globe problem, you know. That problem was, I actually really like that style of problem, but I'll show you kind of other ideas we can use for this, which are a little bit silly, but it is practical. You can actually do it for that purpose. So let's go through this first. Let's start with the first theorem here today. We got theorem 10-1. Now again, theorems, we have to like prove it. You know, it's not an obvious thing. It's not something we take for granted and we just assume as truth. We have to actually prove it. This one's pretty straightforward. I believe it talks about congruent angles, congruent arcs. All right. So we'll get started here. So no name on this one or anything like that. Okay. In the same circle or congruent circles. So what they're trying to explain here is that you can draw one circle, you can draw a couple different ones. Two arcs are congruent if and only if their central measures are congruent. Central measures are congruent. Okay, I'll let you write that down. No name. I thought that was kind of weird on this one. I would have probably called it congruent arcs. That's what I would have called it. But there was no name for this one. Just said theorem 10-1. The same circle or congruent circles. Two arcs are congruent if and only if their central measures are equal. The word if and only if, I'm just going to put this as you, I know you're still writing, but the word if and only if is a biconditional. It's a conditional statement where it uses the word if and then. But a biconditional is when they use the word if and only if. And that means you could actually write the sentence like either way and it would still be true. So what I mean by that, so the first sentence would be the same, same circle or congruent circles. But we could start with, central measures are equal if and only if their arcs are equal. So you could do something like that. But again, it's talking about, I'll just do one picture. That we're trying to show that two arcs on an actual circle, so let's call this A and B. We're trying to show that that arc right there, from A to B, let me highlight that, that arc is equal to this arc over here. Let's call this one C to D. And the only way that this works, if those arcs are equal, okay, it's because their central angles are the same. That, if this angle, let's say this angle is, 15 degrees. That's a little stretching it, but let's say it's 15 degrees. And this one is also 15 degrees. Then it forces these arcs to be the same. The arcs are actually equal to each other. Well, it goes off of everything we talked about last week. The whole purpose of the whole way that this one works is because of that formula that I gave you. S equals R theta. That was the formula we talked about Friday, and that's why I kind of wanted to go into that. This idea, this property about arc length actually proves why this theorem works. That the arcs themselves, the arcs are actually equal to each other because the central angles are the same. And the key word here was that we had equal circles. That for things to be equal, for circles to be equal, their radii have to be the same. So if the radii are the same, then that makes sense. Well, this is a radius, and if you take the angle, which is theta, the central angle, times the radius, that gives you arc length. Well, that should make sense then, because they both have the same radius. Now, whatever that number is, and then we can take whatever that radius is, we take it times the angle. Well, that's 15 degrees times pi divided by 180. And that would be the same for both arcs. because the radius never changed, it was the same circle. So this S turned out to be the same number every single time anyway. And so going backwards and forwards, this is why this actually works. So if you know that the central angles are equal, in my case that's the example I gave you, the 15 degrees are the same, we can prove the arcs are the same. And if I know the arcs are the same, that means the S is the same number in both, then we can prove that this angle had to be the same, because the radius never did change. The radius is the same in both circles. So you could go backwards and forwards. To figure out angles, if you needed to, you could divide this R over. So you could take S, whatever S is, divided by R, and that gives you the angle that you're making. And that would be in radians, by the way. All right, so, but that's the idea. That was theorem 10.1. Pretty easy, but again, it used this theorem, or this property that we talked about on Monday, or Friday, I should say, Friday. Okay? All right, perfect. Let's go through the next postulate here. Let's put it in here. Okay. And this channel is just to let you know you probably are in camera. Just let you know. So you're fine. So, okay. Are we good? Does everyone have the theorem written down? Again, the proof was actually that that simple property. So if you didn't write down that formula that we talked about Friday, the arc length formula, S equals R theta, that was actually the whole entire proof why it actually does work. All right, next one. We have a postulate. Now, postulates we assume are true, but we have to talk about this one. So, all right. So, postulate 10.2, or I should say 10.1. We haven't got to this first one yet. All right. This one does have a name. The postulate name is arc addition. Arc addition postulate. Okay, we'll go through the formula here in a second. So, okay. Here we go. The sum of an arc is equal to the sum of two adjacent arcs. Now, the idea, they use the word sum twice. How I would actually modify this, the measure of an arc. So they want to talk about how you can add arcs together. Fine. The trick is you can actually add arcs together as long as they're adjacent to each other. The word adjacent means side by side. The word adjacent in your textbook, the definition of adjacent is it's when two arcs share a common point. Common endpoint. So I'll give an example. In fact, I might just use the picture I have on the board just to show you how you can add arcs together. So, again, I'm paraphrasing from the book. This definition actually changes depending on which textbook you look at. But the measure of an arc, or the sum of arcs, you can add. If you want to add arcs together, you have to make sure they're adjacent to each other. It's kind of like when you add angles together. So here's the idea. So let me put another dot over here. Let's call this E. We can add A and B and E together, but the trick is how you do that. You actually just add their central angles together. Whatever these angles are, they can be different angles, 15, and let's say this is 10. You can add the central angles together. That's totally fine, because it's arc addition, right? You can add the measures together. So if you had the measure of arc AB, so again, when I put the little M out front, that means like the actual central angle, and you add that to the measure of the other angle, which is the measure of arc BE. And again, these are the angles, so this would be like 15 and 10, that's what those little M's stand for. Then you're going to get the measure of the entire arc from A to E. It's kind of common sense. So you can get the entire arc starting from A going to E, because they did share that adjacent point. right? They're sharing their common endpoints. Again, you can actually do it like this as well. You can flip the letters around, you can, it's still the same thing, so don't feel like the letters always have to be in a specific order. You can flip them around. But the trick is having the middle letters in common, like the B. So that's what I would try to make sure of. Now, the trick is that they also talk about is you can actually add arcs together to make the entire arc. So if I leave the M off the front, that means the actual distance itself. And you can still do the exact same thing. You can add arcs together like this. Like the actual raw distance. So if I actually knew maybe A to B was, say this is, I don't know, 20 inches, and this one is 17 inches, fine. You can add the two together and get a total of 37. So it actually has two explanations. So you can do arc length and you can do angle measure, which I think is kind of nice. But again, the trick was they had to be adjacent arcs. Questions, comments about the theorems we have, or the postulates I should say. That one's probably common sense. Most people know that you can do that. You can just add two things that are side by side to make a larger one. Now why I brought this up is because one of the problems we had, I think it was Friday I brought this up. Friday we did problems where we had problems like this. I think I did an example like this on Friday, where this is angle 1, this is angle 2, this is angle 3, and this is angle 4. And they gave me certain numbers on this picture, like angle 1 here, let's say this is 50 degrees, let's say this is 20 degrees, and this is 35 degrees. Let's say that those are my numbers. Then you can find that piece. You can find the one that's missing. Because it's using this concept, that you can add arcs together, you can add central angles together to make larger angles. Okay, it's a part of the central measures. So like, for instance, what does a full circle have to make? 360. That was I think the definition of a circle that we talked about last week. Well, the idea is that if we know that entirely, like when you add all angles 1, 2, 3, and 4, they have to make 360. You can add specific ones together. So using this concept, I can add the 50, the 20, the 35, and I can make this entire angle whatever those letters are. Let's put some letters on this thing. Let's call this M, N, O, and P. And let's call this Q in the middle. We'll put another point over here. Let's call this R. Now we can find, the measures of arcs. Like if I wanted to find the measure of angle number 4, that's the same as writing the measure of the arc MRP. That's the same thing, because MRP is that central angle. That's the same as angle 4. So there's two ways to write it. They mean the same thing, basically. But what is that? That's 85, 105. So you add 1, 2, and 3, and so if you add these together, that's 105. And then you can figure out what's left, because this has to make a total of 360. So that means, what does this have to be? 255? It has to be 255 left over to add up to be 360. And so it is definitely a major arc. It's larger than 180, so it's not a semicircle. So that's 255. But again, what allows me to do that is this thing right here, that I can add, pieces together, which is this postulate. Okay, questions, comments about any of the stuff we talked about today? Okay, perfect. Let's get to the more practical application process, because I think this is kind of easy stuff. Let's get to kind of a cool one. I want to talk about, bless you, I think last week we did a problem where, we did the globe problem. I want to do a different style problem. Let's do like a Ferris wheel problem. And hopefully this will kind of click on what we need to do here. And I want to talk about how to find distance that you're actually traveling. So, and we can do this for any type of angle. So now that we know the concepts of circles and whatnot, then we can do this for a different application as well. All right. Too well. Okay, so let's say we had a Ferris wheel. In fact, let me just put up a picture up here so I don't have to draw this terrible drawing of it. Let's see. Perfect. This will work. All right, here's my Ferris wheel. Let's see. All right, so let's say you're on the Ferris wheel, and everyone knows, like when you get on the Ferris wheel the first time, it doesn't just start spinning around. You always have to like load everyone on. It takes forever. It takes 10 minutes just to get everyone on. And then you go for like 2 or 3 laps. Then you're done. So let's say you just got on here, and you rotated up to, let's say, this point here. Okay, so you rotated. The idea is that if you knew the angle that you actually traveled at, like if you knew this angle, then you could figure out the actual distance you covered. And that's why, and this is one of the things I always find kind of funny, is that if you actively wear like a smartwatch, like an Apple Watch or Android watch or something like an activity tracker, and it does like elevation and stuff, you can actually throw off your activity that you do that day by riding a Ferris wheel, which I think is kind of funny because it'll know that you're going in a circle, so it thinks you're doing laps, especially if it doesn't know like altitude, like the original Apple Watches didn't. It didn't know altitude, so it would actually track that you're doing an activity, and you would burn a lot more calories that day, which I think was always kind of funny. So if you went at this this specific angle, it thought that you actually maybe ran that distance because it was actually tracking that you're changing position, which I think is kind of funny. So that angle itself, there is. Let's see. There. I don't know what my angle is. So let's just say this is. Let's go 150 degrees. It's not straight across. It's not. Yeah, let's say it's 150. Okay. And let's say the Ferris wheel is a 20-foot radius Ferris wheel, like it's big, 20 feet from there to there. Okay. That makes sense. I mean, this is a person standing here, so maybe a little bit bigger. All right. So let's say it's 20 feet. Now we can actually figure out that distance because we're going to use this formula that I talked about earlier. That you have the radius of your Ferris wheel, you know the angle you're spinning at, and we can actually find the distance you traveled. So the radius, what is that, 20 feet? You take that times the angle, which mine is 150 times pi over 180. 150 times pi over 180, and that will convert that 150 degrees into what we call radians. That's just a different form of measure. And when you actually multiply this gives you that arc length distance. Now, actually typing this on one of my calculators here. Let's see, where's my calculator at? Under. I've got this one. I have that one. Anyone see a really big calculator in here somewhere? Aha! Here it is. That's the one I wanted. Okay. Okay, I want the good. All right. So 20 times 150. We're going to take it times pi, and we're going to divide by 180. I'm going to just type it all at once, and it tells me that I'm traveling. And if this is somewhat accurate, I'm traveling 52.336 feet. So that's the distance I traveled, which might make sense. If you think about that was 20 feet, so we go, 20 feet, 20 feet. So we're past 40, so maybe 50 feet total. So if you think about it in terms of realistic, so you traveled 50 feet, so your activity tracker would mess up that day. You actually traveled further than you think you would. Okay, but here's the concept. The thing was, it wasn't just the initial ride, like getting on and just kind of loading people on. It was the actual spinning that threw it off. So on a Ferris wheel, when you get on, it'll revolute, so many times in, your time. I think you get most times you get 7 revs. You get 7 spins. Then it comes to a stop and dumps you off. Well, if you're doing 7 full spins, so my radius of my Ferris wheel is still 20 feet, but the thing is that has changed now. My angle has. I'm not just going 150 degrees. I did 7 full revolutions. What is a full revolution? 360. So the trick is to figure out this angle. You take 360, which is a full circle, you take it times 7. That gives you what a full circle is, right? But you're doing 7 times over. So that's 0, 42, carry a 4. That's 21 plus 4 is, this is your angle you traveled at. You went 2,520 degrees. you spun around like multiple times. And then the idea is that you have to like convert that back to radians. So you take your 2520 times pi, and you divide by 180. And that will convert this problem down where it'll tell me the distance I actually traveled. And this is the part that I always find kind of funny, is that you're going a long way. Like, just to have you think about that. You did 7 revolutions, in a few minutes, whatever that Ferris wheel ride was. But you actually traveled a lot further than you think you did. In fact, let me actually just do the math here. So you're taking 20 times 2520 times pi divided by 180. I actually traveled 879 miles, or 879 feet, I should say. Feet. And there were some decimals on it. I traveled 800 feet. Okay, just to give you an idea what that is. That's about, not quite a quarter of a mile, it's a little bit less than a quarter of a mile. 1/16 of a mile, something like that. So the idea is that 800 feet, it's a long way, and that's why your activity tracker would actually be thrown off at that point, because it thought you're actually traveling, because you're going slow enough that it doesn't think you're in a car. Because if you're in a car, it knows like to throw those numbers out, because it keeps track like no person's gonna be running 30, 40 miles an hour, so it throws out that data and it doesn't track it. But on a Ferris wheel, it is going slow enough that it thinks you're actually moving, because your heart level, your heart sensors are actually going up. You're spiking. Your heart rate's actually increasing. So it actually thinks you're doing an activity, which I think is really funny. And that was the original watches used to do that. So, all right. Questions at all about the Ferris wheel problem? Okay. So. It was just kind of one of those problems I want to talk about. Now, the other thing is, like, a lot of the times, like, yeah, this is impractical. No one's going to calculate this when they're writing. They're just kind of enjoying their time on the Ferris wheel and whatnot. So I was trying to think of things that were different, that, that it would affect me differently, and things that have affected you differently in your time. And I was trying to think of, like big picture ideas. And one of the concepts that I thought of was music. And let me get rid of this picture. I don't like this picture. Let's get rid of it. Okay, what I mean by music is that music has changed, over the past, 30 years, like big time, if you think about it.
After the bell rings, Reed Ammerdinger, Helen Will, Caleb Anson, Katie Ferris, Chase Wilson, Eric Goss, Dalton Vaughn, come to the office, please.
Okay. These are the 3 topics I want to talk about maybe tomorrow. Talk about the difference and why this math would actually make a difference. LP records, actual physical records. You can still buy them in the store, by the way. Best Buy, they have them backed by the TV department if you can't find them. CDs, obviously, everyone knows what a CD is, and then MP3s, which is pretty much what everyone uses when you do streaming through Spotify or Apple Music or Google or Amazon, whatever you're using. Whatever you're gonna use. These are basically the different formats that I've experienced in my lifetime. I was never really big into cassette tapes. They had cassette tapes. I didn't really use those. There's 8-tracks, which were old school, but these are the 3 that I vividly remember when I was a kid, using a lot. But the math we're seeing on the board is actually directly impacted, these objects. And so we're going to talk about these tomorrow. So it's kind of something that I thought I was trying to maybe pertain it more to you. And we'll talk about computers and stuff tomorrow too, with the same concept. All right, there you go. Bring your books tomorrow. We'll probably have an assignment tomorrow, which will be kind of short.